Yeah.
The Empower Conference is something that I came up with an idea 3 years ago in 2018. And as you heard in the morning, Professor Balakrishnan talking about it, we are now in the third edition. Unfortunately, last year we were not able to do it. Now, with each edition, we have been changing the way or the topics that we are looking at. And this time, one of the topics that we thought would be useful is to focus on locomotor disability, but also to look at a lot of devices. Right? And that is sort of the session that we are having today. It is a challenge. Under normal circumstances, we would have had demonstrations, prototypes. And unfortunately, because of the pandemic, we are being forced to do this online. But I'm hoping that with our speakers today, we will actually get a good opportunity to understand the kinds of devices that are available for persons with motor impairments. In addition, later this evening, we will have another session on wearable technologies, and the two sessions are actually interchangeable, complementary, because it's hard to think of prosthetics without being wearable. So again, although the two sessions have been separated out, given the constraints of being online, we have managed to find our speakers. Our first speaker this session is Dr. Prasanna Lenka. He is the head of the department at the Department of Prosthetics and Orthotics. He's also in charge of the Department of Rehabilitation Engineering at the National Institute for Locomotor Disabilities. I first was introduced to Professor Lenka a few years ago at their conference in the Northeast. Until such a time, I was not actually clued in. And that goes to show how there are pockets of excellence happening across the country. And these conferences help us come together, interact, and learn from each other. The second talk in this session will be a contributed paper from National Institute of Speech and Hearing. And I'm hoping that by then the speakers would have joined the call. And finally, the last talk is another invited talk by Professor Reiner, who will be joining us from Zurich. So we have had to change the order a little bit to accommodate Professor Reiner's schedule in Europe. But overall, I'm expecting that we will have a very good session. So with that brief introduction, I request Dr. Lenka to kindly start his presentation.
Professor Lenka, you are muted.
Thank you, Anil, and thank you all the organizing members to plan for such a wonderful program, which will really benefit to our organization, our department, our ministry, the whole total public. Really, it's a because of time constraint, we'll focus to the topic itself. So may I go to the topic directly without spending?
Please do, please do.
Sure. Yeah, basically, I am from the department where we are the implementing agency or service provider to the persons with locomotor disability. Although we have some training program like physiotherapy, prosthetic orthotic, rehab engineering, some certificate course, but major area of focus is to implement the service required for the person with disability. Indirectly, we are the direct service provider, or you can say we are the hospital where the treatment or rehabilitation program is being undertaken by the Government of India. So different institutions like NGOs, GOs, or regional centers. Already I have been introduced, so may I go to the topic? Yeah. So I hope it will be a series of discussion and talk on technology and disability, where there is no alternative or there is no ambiguity in this regard. Like technology can make the life easier. especially for disability, it is an essential gadget or essential piece of information, knowledge. You can say without technology, it is very difficult nowadays to rehabilitate the disabled persons, and their expectation and the development throughout the world, keeping all in view. This is the right time, or you can say a little bit late also, we have to focus on assistive technology. Basically, as per the definition or prescribed definition, we may say any item, may be physical, may be virtual, it may be piece of equipment or itself a complete product, whether acquired commercially or customized or modified or fabricated by taking the person's choice to increase or to maintain the functional capability of individual with the disability. So there are two things. One is to improve the functional capability. One is to restore the functional capability if there are loss. So you can say it is many ways useful to the persons with disability for the rehabilitation. For an example, if I say, what is ability? It's nothing new. If I say the American Paralympian Stoojman won the silver medal with the right hand transhumeral amputation in compared to a normal person, that means they are more ability. They have more ability. They have shown their excellency in different way. Many of them. Just I showed an example. There are many examples where we will find their ability should not be compromised based on their disability. Some example, the runner blade in prosthetics. It has been seen. It has been documented. It has been tested. The person, those who have bilateral transtibial amputation or bilateral loss of the limb below the knee, they run faster than normal in prosthetic runner blade. So prosthetic runner blade, the person who designed was itself an amputee, Phillips. He thought, why the amputee person cannot play football, cannot play cricket, or can't run. So here is the concept called problem is the mother of all invention. Need is the mother of all invention. He is the person who is basically amputee. He designed runner blade, and now runner blade is very successful. Still, we are also using in your sports cases.
Professor Ranka, I am still seeing your first slide. I think you're talking on your fourth slide. Is that correct?
Okay. So is it fourth slide? Okay.
I think your slides, I'm not seeing your slides change. Can someone confirm if the slides are changing?
Yes, sir. No, the slides are not changing.
Not changing?
They're not changing.
Not changing.
No, slides are not changing.
Okay. So let me.
Maybe stop sharing and start again.
Yeah, sure.
Yeah, now we're on the fourth slide. That's correct.
Okay, fine. Yeah. I think it's in full view. Maybe some problem, so I stop the full view. I hope.
Yeah, I think this is fine. This is fine.
Okay, fine. So shall I continue, sir?
Yes, please do. Please do.
Yeah. So similarly, the national scenario, if I go back to the census 2011, still we have the population around 2.21% of total population with disability. Out of them, almost 50 lakhs require mobility aids only, and 40 lakhs around from the other source, they also require some kind of mobility. During survey, people generally consider those who are disabled or those who are not able to walk, they consider they are disabled. But it has been observed the geriatric cases, old age, diabetics, hemiplegia, post-stroke hemiplegia, lot of neurological cases, they also considered or they are also certified as disabled. So it is expected the percentage will go increase in 2016 population. Around So therefore, around 100 lakhs of assistive technology, assistive device that is required for the present population, or as per the 2011 census, it needs replacement at an interval of 3 to 5 years. So that means the requirement is too high. If I distribute the different types of disability, locomotor comes the highest percentage. It also include multiple disability, also include movement disability and geriatric cases. So locomotor almost, it has been distributed as 19%. It has been 19%. It will go up around 36% if we include all the disability who needs mobility aids. In the world scenario also, it is same. It was estimated in 2003, around 2 crore of population require wheelchair, those who don't have a single one. That means it's a huge device, mobility requirement is huge throughout the world. The market, the business, the commercial angle, if I say, the 2017 or 2018, it is around 16 lakhs 1,141 million US dollar business volume in the world. So it is expected it will grow up to 31 lakhs of million US dollar in 2027. So business wise also is a huge market of assistive technology and assistive devices. There are supports, there are international or national legislation in this regard to support the stake or rights of the person with disability. Even if United Nations Rule 3 specify all the states, all the country, they should provide or they should have provision. Rehabilitation service is essential in order to sustain their optimum level of independence and functioning. Article 25 recognizes the persons as the rehabilitation as their right. Article 26, the states of the country should ensure the treatment or health-related rehabilitation should extend to the person with disability. Similarly, in our country, Section 40, 41, and 42 of RPW Act says access to all means includes transport, building, information should be accessible, or it should be barrier-free. It should be mandatory provision in the accessible norms of CPWD or NIC or transport system. You can say it's completely extended to all. We call universal or inclusive of all. Similarly, WHO, also World Health Organization, they also same thing. 71.8 resolution. They prepared a draft and they propose a focus on global action on assistive technology, GATT. Even out of 195 countries in the world, 60 countries participated in the seminar, or you can say the conference in the Geneva, where it has been unanimously decided the GATT or General Agreement on Assistive Technology should be implemented throughout the world. Something, if I distribute the different devices, we will find around aids for the daily living, or you can say 20% of mobility aids and 16% of the aids of the daily living constitute around 36%. This comes under the locomotor disability. So it's a major portion of the assistive technology, assistive device required for the locomotor device. Yeah, it needs starts from the child. So basically, we all know in disability, it's very tough to walk, very tough to attend the schools, and very tough to do the follow the teaching material because of the problem of because of the loss of limb, or because of the paralysis, or because of the weakness in case of locomotor disability. So we don't have the access. We don't have the access of all schools, college, or you can say building to person with disability or person with locomotor disability. Even if in the growth stage, when the child grows, we learn how to stand, we learn how to sit, we learn how to walk. That process, generally, we all know that process happens automatically. We have a normal brain. But if you don't have the input sensor or the input like what we have the input, or five sensor we have, if loss of any sensor, then entire process will be deformed or process is not complete. So that means we should have very clear facility to have a normal motor development. You can see different challenges in case of high level amputation. This lady report to us with a bilateral accident. With an accident, she lost both the legs in a train accident. Initially, she is not able to stand. She is not able to maintain the center of gravity. Then subsequent the rehabilitation part, we make them stand, make them sit, then make them walk, make them sometime run, you can say. So there are a lot of series of devices which you need in between the treatment process. That also comes under assistive technology. You can see from the picture a lot of device, the conventional device, what we very low cost device, what we provide to make the person adaptive, or you can say biomechanically adaptable to the lost part of the limb, so that the person can use the biomechatronics or mechatronics or exoskeleton or any high-tech device what generally the IIT or technocrats are planning. So before that, lot of devices required to make them technology viable. Similarly, it's not only the cases where we could see in the geriatric. It starts from geriatric, it's to pediatric or from infant. They all need some sorts of devices. I hope what in the introductory section, what Anil sir said, we should have a demonstration or we should have the device specific demonstration, but it's not possible. I'm sorry. So if you want to have some another seminar, I can go device by device, but at a glance, you can see there are different types of prosthetic orthoprosthesis also, or which are mostly mechanical or passive in nature. But there are things which can be automated through a joint or mechanism, which will come later on. Yeah, same from bilateral for trilateral 3-part loss, sometimes quadrilateral 4-part loss. So that they also need to rehabilitate it. They also need life. They need to work and they need to do their daily activity for their household or for their living. Simple child case from post-born to amputation. They also need some sorts of standing device to adopt the post-born or to release the contracts of the post-born. Similarly, for diabetics, for cancer, for non-communicable disease, for stroke, everywhere you will find the use of assistive technology. So yeah, it may be a speech, but it's a fact. There are many people who are not aware of assistive technology, assistive device. Those who even medical fraternity, even if the treatment, the treating surgeons also, because the life can be easy, or life can be more adaptive, life can be more easy to use the function or to use the device or use the information technology, IT gadgets, or any sorts of mechanical device for the day-to-day activity. From starting from standing, starting from running, or starting from the walk, even you can say simple devices, we call it a low tech or no tech. A person can't even for stair climb, he can make a single sorts of stair, which will fit it to a handle. The person can take the handle and take the support. He can move with the investment of only 100 or 200 rupees. But if I say the person can't go to stair, then person will be disabled from the environment. So that means the barrier like washroom or stair, the buildings where you will find many of the disabled children or school children or officers, those are also living with high society, they are not accessible. Yes, a lot of technology, simple technology. It was published in Time magazine. A simple hydraulic operated standing device, or can say walker, is able to make the person walk, stand, sit, so that person can rest in between in the walking process. Yeah, it has been well noted in all airport. Mostly, a simple device can make a bilateral amputee. Those who don't have hand or those who don't have the normal hand, they can take the water. If they don't have hand, then how they'll take the water? Yeah. So I'm just afraid of my time. So there are different devices which comes under locomotor. It may be mobility device, which very populated or very dominating in nature. Means I said locomotor disability mobility device. Many people they have some concept. There are sitting device, there are bathroom device, there are environmental control device, there are ADL. ADL means to cook, to eat, to toothbrush, to comb, to operate the entire spectrum of activity. It's called a device. Prosthetic device overall, the lost part of the body, to replace the lost part of the body that physically lost. Orthotic part, to support the weakened part of the body, like paralyzed, like deformed, like fracture, or like weak part. And lastly, the exoskeleton, which is very nowadays coming up to the field, which will make the person walk with the power device. Yeah, recent advance, we also work that I'll talk on that. Mostly the power wheelchair, the concept of mechanical wheelchair is shifted to power wheelchair. I don't have the time, otherwise I can show video in my clinic. If you find all mechanical wheelchair has been replaced by the motorized wheelchair. Nowadays, people claim, it's surprising to note, basically I'm a clinician, it is surprising to note people demand motorized wheelchair. If you tell them, take a wheelchair which is distributed by Government of India free of cost, no, they want to pay. They want better treatment. They want better mobility. So in our data, we found in 2015, the treatment of free of cost was 90%, almost 90%. Now the treatment against payment comes to 60% of the total population. That means they also need good technology, better life. So all passive wheelchair will be replaced by power wheelchair in due course of time. Maybe may not be all, but majority. Similarly, prosthetic also replaced by mechatronics. Orthosis will be replaced by the functional electrical stimulation or neuroprosthesis. Similarly, robotic will come up. I hope the students, the research scholars, sorry. Rehab robotics, similarly for exercise purpose, for person to physiotherapy, for person to in between treatment period, after accident, before going to bed or before going to the office. Environmental control, a person where he will or she will go back to the home, and how will operate TV, how will operate entire gadgets. So we should have blue. Anyway, that will all coming up. Bionics also. Bionics also is coming a very big way. Yeah. So may somebody help me to monitor my time? Yeah. So this is.
Professor Venkat, I think you can speak for another 10 minutes. There's no issue.
Yeah, sure. Thank you, sir. This is a conventional wheelchair. What I was talking about is a mechanical wheelchair or tricycle we call, because this wheelchair goes outside. Generally, the people known in our doctor group, they call tricycle. But still it's a wheelchair for outside. Wheelchair for inside. All are mechanical. This similarly the crutches, auxiliary crutch, or this. I hope all the students or maybe the department, they well are of this. But okay. Yeah, similarly, the prosthetics, this is endoskeletal prosthesis, this is exoskeletal prosthesis, this is height adjustable prosthesis, and this is a very conventional prosthesis, which we call only the cost is 4,000 for cosmetic purpose, non-functional. Few functions are there. The ease of control, like it will close, it will move by if you pull a cable through body power. So almost this is also conventional and replaced by myotic prosthesis. Just for an example, I saw this due to heavy body weight, due to the ligament injury, the person needs prostate orthosis for the walking purpose. Similarly, hands, similarly leg, or similarly spine cord due to different type of anomalies. And that's one interesting point. If I want, I don't know this. The most of the braces, most of the orthosis, if you say, they comes from name of the city, Milwaukee brace, Boston brace, all from the top developed country city. The 3D brace. So basically, the device is designed, or you can say clinically trial on that city by few professionals. So here, I am sure the kind of talent, the kind of facility we have, if we collaborate, we can do the same thing what other Western country people are doing. Yeah. This is the topic of interest. I hope people are working on this. Basically, we call advanced assistive technology, because if I divide the conventional one, what I've already been discussed or presented, advanced one comes to the control system, mechatronics, electronics, IT or computer system, intelligent algorithms. So that's where we got interest, starting from pacemaker to artificial skin. Everybody, we all are interested in that. So if I call simple a knee joint, or simple elbow joint, simple wrist joint, this can be actuated through mechatronics control. Yeah, for an example, the feeding robot. If you say the robot to allow the person, or if you command a robot, the robot will allow the person to take the food properly. Similarly, for lowering, this is a mechatronics processes where the processes needs the command, needs the information of a prosthetist. That means the user is depending on or depends on a qualified or licensed prosthetist, how to make the cadence, how to make the speed, or how to actuate, or what are the impedance of the cadence control. But if you make it purely robotic, or robot automatically sense through the different sensors, we all know different sensors, and actuate the actuator depending on the requirement of the person or speed of the walking or different cadence. So the damper of knee joint, even if in fact I am also working on this with ISRO, even the damper of knee joint, it ranges from cost of rupees 50,000 to 16 lakhs. So the most commercially available Autobox Genium 4 knee joint cost around 16 lakhs or but 22 lakhs, maybe range of 44 lakhs. So it is not possible for Indians or us or people to afford. But if, honestly saying, the technology cost is high because of the research, because of the algorithm, because of the knowledge. If you go to the electronics part, it's a very simple block diagram. But anyway, it's not easy. There are 6,000 components and a lot of series of programming, and that needs a different session on particular mechatronics knee joint. Similarly, hand gloves to operate the mouse, to operate keyboard, to operate different, depending on the residual movement. If I have this movement, I'll program this. If I have this movement, I'll program this. If a person is not completely paralyzed, if a person is having partial paralysis, he or he should not be discarded, not to able to walk, not to able to operate computer by using the computer assisted technology. Similarly, there are a lot of advanced orthosis which we call exoskeleton or robotic orthosis, which will make the person to walk in case of post-traumatic accident or post-traumatic paralysis. Similarly, wheelchair, yeah, I hope the IIT Chennai also working on that. Wheelchair, basically, people need wheelchair which will walk in uneven terrain, or the village, because rural area is the maximum problem where majority of the populations are there. The kind of wheelchair what we have, the motorized wheelchair, they only can run on the plain surface or inclined surface. It's not fit for the uneven terrain. Yeah, we worked on a.
Priyanka, you have a few more minutes, and then we'll have to open it for question and answer.
Okay, I'll fast round up. Yeah, we worked to skeleton device. Yeah, I think I should go to that device to drop. Yeah. Yeah. So microprocessor control ankle joint, we made an attempt through a DST project to actuate the ankle joint to see the how much benefit or how much physiological cost we got improved through a calibrated measurement. On this experiment, we found almost, you can say, the cost of the physiological cost of the walking reduced by 60% in compared to the conventional processes. So that means a person can do more efficiently, 60% better in compared to the normal mechanical passive processes. Yeah, this device was patented and it's not commercialized, but still the cost we kept only 10,000. It's feasible or not, even it's not still not decided, but still within cost of 50,000, the joint can be manufactured. But if I go to the commercial joint, the cost is more than 2 lakhs. So yeah, this is the commercially available the ankle joint. I hope there are a lot of slides. I think all the time is very packed, or most of the speakers are very busy. They are looking time. I should conclude my session and go for question and answer. Yeah. Thank you.
Thank you very much, Professor Ranka. We will now open the session to questions. I understand that Rida Amjad has a question.
Okay, I have not. Okay.
You can unmute yourself, I hope, and ask your question.
Good afternoon, sir.
Yeah, good afternoon.
I'm a student. I'm working on my thesis. The case is spina bifida, and it has meningomyocele. So in this case, the patient also has a fracture, and one of the goes right from 80 degree to 120 degree. So in this case, they expect a wheelchair. They have a wheelchair.
Rita, your audio is fading.
Yeah.
Can you
Can you repeat the question,
again?
please? Yeah.
Okay. So I'm working on my thesis project. It has spina bifida.
Yeah. Can anybody help me, please? What she says, she want to say.
Yeah. Rita, maybe you can type your question in the chat window because your audio is fading.
Yeah, I have put it.
Okay.
For spina bifida, the patient already has a motorized wheelchair, but now expect an exoskeleton, but one leg move only. Yeah. What is your question? Yes. Yeah, I got it. What is your question exactly? What do you want to ask? Recommendation person. Yeah. Okay. You know, in spina bifida, the case is neurological. It involves the motor neurons. So you should wait for the child to grow, because if you go for amputation, then the paralytic portion or the sensation portion may go up. So it should be decided later on. Exactly, he should be given orthosis to stand with a oil padded, or you can say pressure distributed device, so that the baby will not get pressure also. Immediately she should be prescribed a standing device or walking device, not wheelchair. Wheelchair is very tough. The life will, again, the baby will develop the contracture like tightness of the joint, and baby will depend on the whole chair throughout the life. And still, honestly saying, wheelchair is not accessible to the entire physical environment. So you should give orthosis with oil padded, pressure distributed sensory device. No, don't. It's not recommended for amputation. Yes. What's the age of the child? Age.
14.
Yeah. It's the right time. So may I know the detail? If you can mail me the exact condition or the prescription, I'll definitely guide you. Sure.
Are there any other questions for Professor Ranka?
I don't think. Let me see.
Don't see any in the chat box. I had one question.
Yeah.
So what, and it follows up from what Rita just asked you. See, how do people get in touch? How do they know something exists? How do they know that this expertise exists in your institute in Calcutta? Is there a formal mechanism of any kind that we can think of where people can connect very easily and get such kind of advice without having to register for Empower and listen to a talk?
Yeah, it was a nice one. Even your ministry also expecting a big database, you can say, or the information system where simple Google search or simple chat box can give you answer. We can work on that, the facilities or different modalities. Automatically, it should be from the question answer. The bot can decide or can link to the institution where facilities are available.
Yeah, something
this will
like
be
that
excellent help.
Very useful. Yeah. Okay. Well, thank you very much, Dr. Ranka. I'm sorry that we did not have more time, but it was a very exciting to hear you talk about the work that is going on in your institution. And I always learn when I listen to you. So thank you very much.
Thank you. Thank you all. Thank you.
Our next speaker is Amrita. And Amrita is at the Kerala State Institute of Design. And their contributed paper is on the design development of an adaptive chair. And I am echoing.
Yeah, there's an echo.
So I will stop talking and maybe Amrita can start.
Am I audible, sir?
You are.
Yes. Okay. Good afternoon, everyone. Thank you for
No,
having us.
Amrita, I think
and,
you are echoing.
giving us this opportunity.
I would perhaps suggest that you turn off your speaker and let your microphone do the work.
Am I audible now?
Yes, yes, you are.
Thank you so much. Thank you, Team Empower, for having us and giving us this opportunities to present our project title Adaptive Chair for motor design for and development of an adaptive chair for children with motor disabilities. Can I share my screen right now?
Yes, please go ahead.
So we are a team of 3. I'm Amrita from Kerala State Institute of Design, Kollam, and Alok Krishnan also is a part. He's also from KSID, and Dr. Akhila Surendran from NISH was our guide. And so let's begin. How we started this project. There was a boy. We call him Ramu. He's a 8-year-old boy. He enrolled for communication therapy at NISH. He usually sits on his mother's lap during the therapy session. And his mother, that time when he enrolled, she was pregnant. So she was not able to carry him all the time. It was very difficult for her to carry him and do the sessions. So from this problem, like how we can solve the problem, how we can keep him in a proper position and make the life of her mother, life of his mother a better, better. So one minute. For motor disabilities, these are classified into 5 categories. The first level, in this picture, you can see the first level, the child can carry himself, like there is a small. In the second level, from first to fifth level, there are the fourth and third level. The fourth and fifth level. Fifth level is completely dependent on someone or wheelchair. He need full support. That person need full support, and we are focusing on the fourth and fifth level. And these are the existing products in the online market. You can see the first image shows we got this image from online, and this cost around 5,000 to 6,000 rupees. And the second one is around 20,000. And the third image is from an outside, an international company, and it's cost around more than 1 lakh when it comes to India. So most of the designs are Indian design in Indian market are very bad design or poor quality, and it's not fits for everyone. Like if the child grows, the chair, like it won't be useful for the child for the future. Like after 2-3 or 1 year or 2-3 years, children grows fast, so it's not easy for them to stick on in same chair. Like it's not a proper supportive. And good quality, we can see the good quality ones are very expensive. So we had interviews and observation and meeting with experts. We went to Composite Regional Center, Caricat, and DEIC, District Early Intervention Center in Kozhikode, and IMHANS, Institute of Mental Health and Neurosciences. And we met the physiotherapists, occupational therapists, and speech therapists there. And we met around 10 children and their parents with motor disability, and some of them are having multiple disabilities, and most of them are completely dependent upon their parents. They cannot do any work their own. This is the girl first we met. Her this is the chair which is given from a government scheme. She got this from government scheme. She's 16-year-old. This is the same chair designed for everyone. They are taking the measurements, but you can see in the first image, it is not like, it's not supporting her at all. Her hips are like, her legs are coming out, and she cannot keep her leg properly. And there was an activity tray also, which is because of her scissor gate legs, she cannot keep her legs properly there, and it hits on the activity tray, and it was very painful for her. And the edges are so sharp, sometimes she get hurt. We don't she moves her hand here and there, we don't know how they are moving, so it's very easy to get hurt. The second boy is he had this chair. He doesn't like to sit in this at all because he's not comfortable. You can see the position of the chair. In the previous one, there was a small angle. In this one, you can see that it was straight, 90-degree. So sitting in, he hesitated to sit. He used to get seizures, and he doesn't want to sit in this at all. All the time he wants to sit with his mother's lap. And so it makes the parents or caretakers very difficult for them to take care of the child the entire day. They have to give the entire attention, which is not like easy for them. They have to go do some other works or household work. So it's very difficult for them to take care of these babies. Next, the existing problem we find out from the we have conducted around 10 case studies. We have met them, the children, and what they have got from the government schemes. This is the first image. You can see this is also given by a government scheme, and this boy is very fat, and he's not able to sit in this chair at all. And you can see the angle. There is no angle adjustments or the leg adjustments, so it is difficult for him to sit in this one. He doesn't use this chair that much, like from the beginning, like when they gave it to them, that time only they just used. And the second one is a normal wheelchair. This boy's parents are a little bit financially better, so they bought a wheelchair for him for mobility, taking him from one place to other, like to go for the sessions and hospitals. From my research and case studies, I have found that each cerebral palsy child, we started from cerebral palsy, then motor disability, each child is different, their needs are different. Most of the the adaptive chair makers in India are not considering the aesthetic part and comfortability of the clients. They just make the chair, like they take the panels and cut it and paste it, lines, give it to the people. They are not even considering the like functionality or the angles or anything like that, or the comfortability of the client. And the adjustability factors are most of the chair, you can see that it's not there at all. And if the chairs are adjustable, then the cost is very high, which is not affordable by a low income family. And the materials are the sharp edges, and it should be easy to clean and at least durable for 5 years. So it will be better for the parents, like if they invest in at one time, so it will be helpful for them, like for a long run, it'll be easy for them. So our design brief for to create a seating system for children with motor disabilities that is customizable as per the requirements of the child and cost effective. So from our process started from like ideation. We have created a random. We have generated random ideas. We just started from sketching seating and different types of seating, what all adjustment, and from there we categorize these every idea into 4 parts. It's called COCD method. In this method, we divide the ideas in like, is it feasible or non-feasible? And if it's feasible, it's in 2 categories. If it's very, very easy to make, or if we need some more things. So non-feasible, we can think in future we need some more technologies to add. So these ideas are categorized into four. From there, we will take the feasible ideas we also take the combined 2-3 ideas and generate 4 ideas. I have taken the 4 ideas shown in the final ideas after COCD. These 4 ideas are then go through the SWOT analysis. In SWOT analysis, we check the strength, weakness, opportunities, and threat of these each and every idea. From there, we select the best idea. That is this. You can see the refined concept. So from that, we have taken the reviews and suggestions from the experts. We have made the small mock-ups of each final concept, and we have consulted these experts, and we have got some suggestions. So our final idea was to it's a seating with some adjustments and with an activity tray. So from the experts, we got suggestions like that. Like there should be an angle. Like you can see that in this right side picture, you can see the seating. And this is the 90-degree one, and there is a tilt in the backrest. You can tilt the angle. So 130, 150, we have given the angle. So it is easy for a child to lie down. And the fourth image is this is for the hips exercise, the hips strengthening hip exercise. So if we you can see this angle is the length, knee position is little bit up. So it will strengthen your hips. And the 7th image, you can see these are for the knees. So the force will come to your knees in this area, you can see. So these are the angle adjustments we have to give for these children. So it will be easy for them. And they need a partial head support and a trunk supporting belt, which helps the child to sit in a proper position. So it should be easier for the child will be staying in this adaptive chair at least for 2 hours. So it should be easier for them to move easily. And they need straps on the knees to keep the knees on position, and the child should feel safer. And these are the explorations of different mechanisms we have gone through for the activity tray and the head trunk support and neck support. Next is some mock-up, 1:1 scale mock-up we have done in corrugated cardboard. And you can see we have added the activity tray. And this is the activity tray height adjustment, and this is the seat adjustments. This is the neck support, and this is the for the footrest. This is the footrest. We have taken this 1:1 scale mock-up to the experts again. Then we got some suggestions that angle of the backrest should be adjusted, like a little more tilt, and seating should be like it can be movable from, and footrest height of the footrest should be adjusted different height, and there should be straps and leg separator. There should be a leg separator. And activity trays, first we designed the activity tray in a rectangular shape, and it should be in a more curvy shape, so the child should feel safe. This is the improved design, the final one. But you can see that all the adjustments, backrest adjustments, you can see the neck supporter and the trunk supporting belt, and the leg separator is here, and the footrest. And this is the adjustments for the activity tray. This is the seat adjustment. You can move the seat front and back. So mood board, we have chosen a very happy mood board. So most of the design you have seen that like colors are very dull. So the people will feel that there is a taboo that, okay, the child is very sick or is not well. So when you see a child sitting on our adaptive chair, you should feel happy after seeing that others also feel happy. So we thought like we'll consider the caretakers also, secondary users also. So, and even the child also feels happy. And we have chosen the colors, very bright colors, and we have the attributes are happy, friendly, safe, and caring. These are the form explorations we have done for the side panels. The forms are very inspired from the characters, animal characters, and all the forms we chosen like a curvy one, so that it feels safe, not the sharp one. So that it's a very safety and caring feeling. So material exploration, we have chosen the materials which is available in the market, like local market. So you have used plywood, and these are the bolts we have used, and the wheels we have used, and for the upholstery we have chosen soft upholstery, so it is not sharp, it's not heavy, like it's not hard. The child should feel like very comfortable.
What?
Amrita, you have 5 minutes
Again,
left. You may want to wrap
okay,
it up.
okay, sir. Okay. This is the mock-up correction we have made, and this is the final 1:1. The final design in CAD. So different stages of prototyping. This is the final prototype we have made. So the seating is adjustable. So you can see the seating is adjustable, and the backrest, neck support, and the trunk support. Side panels are all with safety edges covered with foam, so the child won't get hurt. And the edges are given, edges are supported by safety edges. And footrest, you can see the belts. There are wheels also, and the bottle holder for the for them to keep their bottle. And the working. This is the working, how the knobs, we can adjust the height of the activity tray, and this is the handle, we can push the adaptive chair, and some bolts. So this is how the adjustments are done. So we have done the short-term testing on 2 kits. The suggestions we got from them, the parents are the structure is very heavy, and so we have to reduce the substructure, and it's not easy to pull because of the heaviness, and it's not easy to pull that one. And the trunk support should be little more better, and the hip belt, there should be a hip belt. And and long-term testing we have done in 2 months testing. This is a boy whom we did started this project, and he did a better job. Like, he started doing his speech therapy very before he is not able to press this Big Mac. Now he started to press and call his mom. So and the problem was, we identified the problem was the trunk support. It was not a strong one to support him, keeping him on place. And the angle adjustment, he had some issues with the backrest. So the future direction is for from the experts, we got some suggestions that they form more. We have to do the more form explorations and size of the wheel. So because it's a very small wheels we have used, so we have to use a bigger wheels, and the placement of the wheel, it's far from each other. So it should be in a little bit nearby, so it's easy to move around. And handle, the placement of the handle, we kept the handle in the middle, so it should be in a proper position to push it properly. And weight of the entire structure, it should be reduced. And backrest of the angle, as I said previously, it should be in one more angle. If it's there, it will be better. And the trunk supporting belt, the knobs, the materials of the knobs, it is good for the condition at Kerala, but it won't be good for some other place, which is the material can be melting can be happen. And the cover backrest, there is backside of the chair is not covered properly, so it should be covered. If the child is having a sibling, there is a chance the child go inside this space. So thank you.
Thank you very much, Amrita. That was a very interesting talk on the process of development. We have time for a quick question. We have our next speaker waiting, so I'll take one quick question if someone has it.
Hello.
Yes, go ahead.
Yeah.
Hello.
So I had a question. In cases of spinal bifida, will this chair work, and what all modifications do we need? Because in spinal bifida, you will have a lump coming out from the lower back region.
Okay. Actually, I didn't get what is spinal.
Spinal bifida. Spinal bifida is a condition where the spinal cord is not it's not inside the body. There's a part of the spinal cord in the lower back region which comes out like a.
Okay. Okay. So this chair is basically a structure, so we can be customized for anyone. So if the person is having such difficulty, there should be a support in the seating, right? So something should be kept inside, like I don't know exactly what we have to research on that. That's particular. We have to research on that particular problem and identify what is better for that particular person. So we have to which position or which material we have to place on, keep on that particular patient on. So are you getting what I'm saying?
Yeah, I think that's actually, so I guess I think one of the main takeaways is that these chairs are not really a one size fit all, and they have to be customized. And so the platform that you develop has to be customizable, so that the next person who comes in with another kind of impairment and needs some modification, the caregivers in that geography can make that modification easily, because the platform has been set up to be a little more customizable than any standard wheelchair that is currently available or standard platform chair that is currently available in the market. Did I summarize that? Yeah, very good. Thank you very much.
Yes.
Please do reach out to Amrita if you have further questions. I see Professor Reiner has joined us. I'm very excited to have him on board. It was difficult. I know he was traveling, and given the time difference, it's currently morning before lunch for him at Zurich. Professor Reiner has been working in biomechatronics for more than 20 years now, and he's very popular for his cyberthons. And we've heard many good things about the work that he does. And so without further ado, I will let Professor Reiner speak to us.
Thank you, Anil. I hope you can hear me well. Thanks
Yes,
for the invitation. And indeed, I just made it to Lucca in Italy to give another talk in 2 hours. And now I'm happy to give this talk. I hope the technology works. I will also try to show some movies at my talk. So now I'm sharing my screen and starting the animation in order to speak about exoskeletons in rehabilitation. One of the main target groups in our work for people using exoskeletons are stroke patients. Stroke is a very common disease. About 16 million cases are there worldwide every year, and age is a risk factor. So the older people are getting, the higher is the risk to get a stroke. And in many cases, most cases, a stroke leads to a paralysis, to a hemiparesis or hemiparalysis, where half of the body is paralyzed. This requires treatment, therapy, physiotherapy, occupational therapy. However, the patients are most of the time are passive, because they cannot do all the time physiotherapy or occupational therapy. So about 90% of the time they're lying in bed, they're sleeping, they're eating, they are talking to people, they are watching television, which is also maybe important, but not beneficial to the learning or relearning of movement, of gait, of arm movements, of grasping functions. We know that we need a higher intensity of training. And we know this, for example, from children. When they start to move, to walk, before they walk already, they do up to 26,000 leg movements every day. So when they're lying supine, they are moving the legs like this all the time. And that, of course, forms their neuroplasticity and the pattern. They learn the movement by this. When they start to walk, then they're still doing 14,000 steps every day. That's a high number. We need to go shopping, jogging or hiking to get to this number. And with upper extremities, they're doing a lot of reach and grasp movement. In the age of about 12 months, more than 2,000 reach and grasp movements are done with the hands and the arms, which further forms their capability to move. And still, it takes several years until they can do very secure movements. Consequently, we cannot expect that patients who suffer a stroke or any other kind of neurological disease, that they relearn movement after just a month of physiotherapy done, let's say, once a week or once a day. That's much too little. We need to get to higher intensities. For this, we have several devices, exoskeletons, for example, like the Locomat, which help people to make the training intensity higher, to do more training. And we can combine that kind of training with virtual reality, with games to motivate the people, the patients, and in this way also get a better outcome. So there are different kind of versions of these robots. There are robots which are exoskeletal devices, like you see here. The Locomat is just one out of a list of devices. Many of these devices are not commercially available, but they are available only in research labs. We also have some devices which are end effector based, where the foot or the ankle or the lower leg is connected to the end effector of a robotic machine in order to move the leg to produce a gait-like pattern. Both devices show similar effects. However, the end effector based approaches are a bit simpler, easier to mount, but not so secure with the knee joint. The knee can hyperextend or move in an unphysiological way that needs some more personal effort to control the knee joint movement. So there are several studies showing that that kind of training are indeed beneficial. So Mehrholz, for example, did this Cochrane report 2017, where they found that the kind of device does not matter so much. That study was based on 36 randomized clinical trials involving almost 1,500 patients. And what they found out is that it matters if the patients are subacute or acute or chronic, and if the patients are ambulatory or not ambulatory when they start to move. And they found out, especially if the patients are non-ambulatory, so then that they usually need a wheelchair, for example, for that patients, there's a quite clear benefit of that kind of training. Let's go to the upper extremities. Also there we have exoskeletal devices like the Armin, which I have developed in my lab in the last 18 years in Zurich. And we have also other exoskeletal devices, whereas the Armin was the first exoskeletal rehabilitation device existing in our community in the world. But there are, in the meantime, more devices available, mainly also in research labs. And we also have end effector-based robots like the MIT Manus. That's an older device from the 90s, very famous and successful to support also arm therapy in especially stroke patients. And there's also another study from Jan Meerholz from 3 years ago showing a very beneficial effect that was based on 45 trials with more than 1,600 participants or patients. And they showed that robot-assisted arm training improved activities of living scores and also arm function and also arm muscle strength. And this quality of the evidence is very high. So that was about some exoskeletal which can be used for therapy, for training. These are usually bulky, heavy devices because the patients are getting to the clinic in order to get this training, in order to improve body function. Another big field in our research and development is the use of such kind of technology for daily assistance. For this, we need to have more lightweight systems, mobile wearable systems to get in a support for the people in daily life. It can also include a therapeutic effect, but mostly I'm focusing now on an assistive effect. So it's an exoskeleton can be an assistive device, as well as a wheelchair can, or crutches, or a hearing aid, or anything else which assists people in daily life. One device which is also in this borderline between therapy and assistance is that device Andago from Hokoma, for example, which allows to also make the people more mobile. It's not an exoskeleton, but still a device which can assist people in daily life and by making them more mobile. That's another device, a very famous exoskeletal device, Rewalk from a famous company from Israel. And that's a picture which was taken at the London Olympics 9 years ago, where a person with hemiplegia after stroke, no, it was, I think, a spinal cord injured patient, was very successful in participating in a marathon. It took her, however, 60 days to complete that race, but she did produce a lot of media reactions because it was a great step at that time using such kind of technology. There are many more devices available in the market from Japan, like Honda or Cyberdyne, but also from New Zealand, Lexbionics, and the United States, like Parker or Exobionics. Many more devices exist in research labs. And most of these devices are bulky devices, are rigid, are quite heavy. That can have advantages because the devices can be made quite strong. And since the devices are rigid, the weight and the forces are transferred via the device and not the bones and joints of the patient. That's a big advantage. However, there are also disadvantages. The devices are very bulky and heavy. There can be misalignment at the joints, which can lead to discomfort, and the device can collide with the environment and damage the environment, for example. So that's why we focus on soft robots, on soft exoskeletons, on exosuits or exomuscles, as we call them. Connor Walsh was one of the first developing such kind of exosuit, as you see on the right side of this picture. And we developed a new device with a different target scenario. Our scenario was not so much for soldiers, for example, as the one from Connor Walsh. He made a device which was mainly for walking fast. And we said we need to support gait at all, to walk slowly, to do some weight support. And for example, to allow people to use a wheelchair still. Because a wheelchair is a great device. They are affordable, they're working well, the people don't need a lot of energy to propulse at even terrain. But sometimes when there's a step, there's a challenge, because they need to maybe get up from a wheelchair and get into a bakery. And then they can enter the store, they can look somebody to eye level, they can take something out of a shelf, and then walk back to the wheelchair and drive again. I think the perfect solution in the midterm and long run is a hybrid solution where we apply wheelchairs together with exoskeletons. But for this, the exoskeleton must be small, it must be fit to the patient while they're sitting in the wheelchair. And then we also don't need so much energy, because just sometimes we need to use the exoskeleton. So we started with a new design, and we said, let's make it very simple at the beginning and lightweight. The simpler, the more lightweight we can make it, the less power we need. We try to use just one motor per leg, so 2 motors overall, but still to actuate several joints. So we could apply a motor which produces torques at the knee joint and the hip joint and the ankle joint if you connect them somehow with some kind of gear technology or with cables. So we used a cable-based approach, and we asked ourselves, how do we have to guide the cable around the hip joint and knee joint to produce a joint torques, a joint synergy, a moment synergy, which is useful for gait and for stair climbing and for standing up and sitting down. So if we have a cable, we can only produce tension torques or tension forces around the cable, around the joint. So we can only produce one joint extension torque at the joint, or one joint flexion torque, or no torque. So we have 3 options per joint. And since we have 3 joints which are relevant, the hip, the knee, and the ankle joint, we can make 3 over 3 options. So 3 to the power of 3 gives us 27 possible solutions to produce only hip torque, extension torque, or hip and knee extension torque, or hip and knee flexion torque, and so on. And we thought, what is the most important gait physiology? Where do we need what during gait, during stair climbing and standing up and sitting down? And we found several useful phases of gait, but the most promising one for us was the beginning of the stance phase, the first half maybe, or one third of the stance phase, where we have the unloading phase or the loading phase. Here we need to produce anti-gravity torques, especially at the knee joint and the hip joint. In the middle curve, you see how we get a lot of a high knee extension torque and high knee flexion torque. Sorry, it's a high hip extension torque and a high ankle torque. As I try to use my cursor. So that's here what I'm now mentioning, high hip extension torque and rather high ankle torque, a bit higher than the knee torque in average. And that's what we can stimulate or support by providing torque. We are finally supporting the gluteus muscles, which are extensor muscles for the hip joint, and the quadriceps femoris muscles, which are also extension muscles for the knee joint. And we can provide this by guiding the cable in this way. The cable must go behind or posterior the hip joint and anterior the knee joint. And the ankle doesn't need so much support. So here we do not need to provide the cable. And the first solution looked like this. You see how the cable was guided. At the ankle, we're just anchoring, we do not produce a torque here. And then we have the cable in the front of the knee to produce extension torque when the cable gets shorter. And here behind the hip joint to get extension torque at the hip joint. At the first solution, we provided the motor at the foot or the lower leg to keep the back free so that the people can still sit in a wheelchair. But later we figured out that that's not a problem with inertia, but with the weight. To lift the leg, that was not supporting so much. It was, of course, a problem. And that's why in the new version, we placed the motor at the back. Here's another view how we provide that technology, how we made this. We have 3 layers. There's a garment layer at the deep layer, as a deep layer, right at the skin. Then we have a ligament layer here with passive ligaments to produce also a little bit of extension or flexion torques. Then we have the power layer with the cable, which produces the mentioned extension torques. That's the first version of the device with the PhD student Kai Schmidt, who made this. And that was the second version of the device. We could provide up to 400 Newton in the cable, and that gave us about 1/3 or almost 1/2 of the required maximum torques. But these torques were enough to support gait also of people with more severe paralysis. That shows the basic principle actually. We used IMUs, inertial measurement units, to detect the inclination angles of the thigh, the trunk, and the lower leg. And as soon as the inclination is bigger, indicating that there's too much flexion, for example, when the patient is falling due to gravity, joints are flexing, and the IMUs are recording this, and then the motors are getting active and blocking it. You see, he's getting blocked, he cannot fall further. That's the basic idea. We support extension torques to avoid flexions, to avoid falling, to support gait when the loading response at the beginning of the gait phase, and to also support standing up or walking upstairs. We did many kind of testings for different kind of movements, as you see at the green part above. We did many kind of recordings. Inside the machine, we have a lot of sensors. At the beginning, even 4 sensors, and now it is kinematic sensors, IMUs. We also did lab sensing by ground reaction forces, by motion tracking system. We measured metabolic costs in some studies, also cardiovascular responses, and let also fill out the patient questionnaires. In this, we could validate the technology a lot. We were also happy to found a company, a startup from ETH, Meyer Swiss. And Kai Schmidt is now the CTO of that company. My former postdoc, Jaime Duarte, is the CEO of the company. That's a later version of the device where we have placed the motor already at the backpack, and we anchored the device at the ankle joint. And it's another view you see here from the side with the cable, which is actuated from the tender motor unit here at the top. And here you see now a walking of a patient with muscle dystrophy. And on the left, you see it switched off the device, just in the transplant mode. And the right-hand side, it is switched on, which allows a much faster walking speed. That patient could even join the Zurich Marathon 2 years ago. Not fast, but he could walk about 6 kilometers, just a part of the marathon, of course. And normally he can just walk hundreds of meters. So he can do it much longer. And he's using it at home privately. He can put it on himself and put it off again and use it to take a walk with his wife. So you see here how easy it is to mount the system. It just takes a bit more than a minute or 2 minutes. On the left, that's the experienced supporter to put it on to a patient or to a healthy subject in that case. On the right, there's a novice doing it the first time, and both of them don't need so much time to put it on. And we even simplified the anchoring at the moment in the newest version. As you see here, there's no connection to the shoes required anymore. And now the left one will finish soon in 1 minute and 51 seconds. And the novice also finishes in a very good time. So this makes the acceptance very high also of the patients, but also of people using it in therapy units in hospitals. That shows the status of the tests till a year ago. More than 450 patients did test the device. It was sold to many different labs, mainly to labs or hospitals for therapy, but also to, in the meantime, to 15 patients who are using it privately as an assistive device for daily life. And we have used it for patients with many different kinds of pathologies, not only muscle dystrophy, but also spinal cord injury, MS, Parkinson, different kind of plegias after stroke and traumatic brain injuries, and also patients with orthopedic impairments. And now we started a new collaboration with the Charité in Berlin, with the biggest heart clinic in the world, with patients with heart failure, because heart failure can lead to dyspnea, so shortage of respiration, of condition, of endurance and fatigue. And this leads to little training intensity, to less and less training. And this way there's a deconditioning, which is increasing dyspnea and fatigue. So we try to get out of this devil's circle in order to allow training, to improve the endurance of these patients and work against fatigue. And that's the study we started at Charité with 10 subjects so far in a very first feasibility study. And that worked very well already. And now we're starting a clinical study these days or weeks at Charité to further get some more evidence. So that's the idea of the use of that device. It's a clinical therapy device, but it's also possible to use it for home use and for daily assistance. We also go to the upper extremities with the same principle. We use cables, one motor per limb, to support especially lifting the arm against gravity for patients with muscle weakness. And here we have to deal with another problem. The shoulder can get unstable. You see that the clavicular can turn out when we don't take care. That can harm the body. It can be painful and block the range of movement as well. And you see that how it can look in a patient with muscle weakness of the upper extremity around the shoulder. And with a passive orthosis, we can work against this. We used a special BOA mechanism to provide tension. It's just passive, but the therapist can adjust it to produce a pressure onto the clavicle and avoid this kind of instability. And that is allowing already, that passive structure allows already higher reaching movement of the upper extremity in this kind of patients. And we are combining that technology soon with an active part, with a motor, which is driving the cable to lift the arm, support the lifting. And that's how the device looks at the moment. It's a lab device, so it's not that variable yet because everything is mounted in the box, but we know it from the Maya suit, the other device for the legs, that we're able to mount it, to make it smaller and mount it to a backpack. Last but not least, I want to show you a general challenge and guide you to the idea of the cybathlon. I saw in my daily work that there's still many challenges in the development of assistive devices for daily life. The devices are not that accepted. For example, the control of the device is an issue. How should the motor know what the user wants to do? Motor intention detection is an issue. And also battery power is an issue. And also weight is an issue. Also price is an issue. Accessibility in countries which are less wealthy, I would say, that's also an issue. And that's always what we want to take into account in a big event called the Cybathlon. The first one did take place 2016. And that time we even had teams from India joining with a rattan prosthesis. They made it even to the final race. It was very impressive. So the technology not always have to be expensive to be successful. And the tasks we are doing here are related to daily life. It's a bit like the Paralympics, but we're not searching for the people who are the strongest and the fastest. We want to award those who are able to provide, who are able to do the activities of daily living with technology. And we give an extra award in the future for those devices who are very ergonomic and also economically affordable. That was a team from Korea joining a race, a discipline, exoskeletons. We have 6 disciplines, also devices, races with powered or unpowered prostheses, leg prostheses, arm prostheses, powered wheelchairs, which are able to also mount stairs, climb stairs, or a bike race with completely spinal cord injured patients using electrical muscle stimulation, and a brain-computer interface race where the pilots are driving avatars in a screen, in a game. We had a lot of media interest from all over the world, newspapers, and also scientific journals. We did publish the event and also the technology presented by the different teams in different journals, including Nature and Science. And we did also get a nice award. For example, at BBC, there was the most striking picture of the year was from Cybathlon. There's a stamp about the Cybathlon. We went to the Guinness World Records book 2018. And now in September, there was just a new issue of the Guinness World Records book 2022, where the Cybathlon is again mentioned in that book. We got several awards from Yahoo. We got the European Excellence Award and the Oscar of Education, the Global Education Award in 2 categories. Even President Putin, I'm not a fan of Putin, but nevertheless, he was also mentioning the Cyberthlon, and he's supporting the Russian teams. And thanks to Putin, there will be a race also in 2 years in Russia, in Moscow. There will be a small version of the Cyberthlon taking place. So the next event did take place last year as a global edition. We are organizing the Cyberthlon, the next one for 2024, again in Zurich. I hope also some teams from India will join, and I will show you soon a short movie about this. But at the event which we had last year, which was an offline, or no, it was an online event, but people were decentralized participating, some in Zurich, some in Moscow, in Hong Kong, in Bangkok, in South Africa, and so on. So we had 51 teams or pilots from many different countries, and we had online connected everything. The races were recorded a day before, but then we did show them, we did present them live, and nobody did know the results. But then they saw which pilot was the fastest one, and was still very exciting, and a new format which we created. And with this movie now, next slide, I show you how that event did take place. It's just a 1-minute movie now. Thank you for your attention.
Thank you very much, Professor Rainer. That was absolutely fantastic. It is always wonderful to see what technology can do to help people. Maybe the audience has a few questions, and maybe we'll take a few of them. Does anyone have any questions?
Good afternoon, sir.
Please go ahead.
Yeah. So it was an amazing experience to learn many things from your product. So as we could see, the exoskeletons were supported on the lower part of the back. So for those suffering from spinal complications like scoliosis or spinal bifida, what are the things which could be done, as the reaction forces would be sent on the spine?
Yes, thank you for this question. If there are problems with the spine and the vertebra, the back, which hinder the wearing of the backpack of the exoskeleton, it might be an exclusion criteria at the moment. For most patients, we did include a large range of different pathologies. There was not a problem. But still, it's not the most comfortable way to sit at the wheelchair or a car seat or any other seat. And I would be eager to somehow improve this, to either place the backpack to a much higher level or to the front if possible. But then you have a problem if people are a bit more obese, that it doesn't work that well. So it's a challenge to mount the backpack or to mount the drive and the computer at the right place of the body.
Thank you, sir. Sir, we are actually currently designing an exoskeleton for people with spinal complications, actually for the final year thesis. So we would love to get your valuable inputs and insights. Would it be possible to contact you, sir?
Sure, feel always free to write me an email. You find my email publicly on the internet.
I'm sure I will also be able to share it with them. But
Sure.
yeah, I think one of the joyous things about working in this field is that geography has no boundaries. So I mean, there are people across the world who suffer from similar ailments and at different stages of their life. And it's always very rewarding to see how small engineering successes translate into improved quality of life for many such people. So yeah, absolutely. I think if we are able to facilitate through our interactions more collaborative work between your labs and the labs in India, I think I would definitely encourage a lot more of that.
Yes, thank you. I'm very happy if there could be some collaborations. We get, by the way, many students studying robotics at ETH Zurich from Indian IIT institutes, and we still searching for teams from India who are working on cybathlon races, who bring any kind of technology which you might already have. It can be prosthetics and wheelchairs, if they power the wheelchairs, but the prosthesis can be passive. And you don't have to travel. Even you can do it remotely in your country, in your city, and create an online connection so that we can broadcast it to the next Cybathlon 2024 or to one of the series which will take place early. So please contact me or the head of the Cybathlon Executive Office, Roland Siegrist.
Definitely. Are there any other questions? I see there's an extension of the question. Go ahead, Rita. If not, let's thank Professor Rainer again. We will use the sign of thanking.
Thank you. You're welcome. Thank you for inviting me.
Thank you very much. Okay, so I take this opportunity to thank the audience for the session.